65 kilogram skier is gliding at 1.9 meters per second when he starts down a slippery slope of 13.3 degrees, and he travels 61 meters. What is his speed at the bottom? So this is he's basically skiing down a hill or an inclined plane. So like if we were to redraw this, it would look like this. So here's the guy skiing. Here's the angle. So and this is and then he travels 61 meters. This which is the hypotenuse. So remember that we can actually use what's it called? We we could either do this in two ways. We could either use conservation of energy to like find the height here by using 61 meters times sine of 13.3 degrees, and then use conservation of energy from there, or we can use work. So what I'm going to do is I'm going to use work done. So the net work done is equal to the kinetic energy, the change in kinetic energy, or kinetic energy initial or kinetic energy final minus kinetic energy initial. So be careful when you're looking at the forces acting on the skier. So recall from the inclined planes in the forces unit that there's a force mg, but it also has components, which is fgx and fgy. So, and this would be the angle right here. So fgy, which combats the normal force, is mg cosine theta. Now, fgy isn't actually causing the displacement. It's fgx that's causing the displacement, which is fgx equals mg sine theta. So yeah, be careful. Like, it's not always going to be cosine. Just remember, like a good rule of thumb is that it's always the force that is parallel to the displacement, which is down here. And fgx seems to be going the same direction. So what we can do now is, and since there's no other forces, and it's very slippery, so we're just assuming frictionless. So this is our only force. So basically, we can just multiply that by the displacement. So W net equals FGX times displacement. Now I'll give you the net work. And then we can plug it back into the work energy theorem. So the net work done equals 1/2 mvf squared minus 1/2 mvi squared. So we know the initial velocity, so we're gonna add 1/2 mvi squared to both sides. So then it'll cancel on this side. So W net plus 1/2 mvi squared equals 1/2 mvf squared. So we can multiply by 2 on both sides, so 2w net plus mvi squared equals mvf squared. So I'm gonna on. So I'm gonna rewrite that a little bigger. So 2w net plus mvi squared equals mvf squared. So we can divide both sides by m. Let's get vf squared. And then you square root both sides, so you get the square root of 2w net over m plus vi squared equals the final velocity, which should turn out to be around 16.7 meters per second. Here's our next problem. This is a graph. So this is F versus X, or a force position graph. So we have, so basically what the car is, it has an initial force of 10,000 10,000 newtons, and then it gradually goes down to 0 once it reaches 200 meters. So what we're trying to do is we're trying to find the final speed of the car. So recall that work is integral of force with times dx, and this is in calculus terms. So, but at the same time, work is also the integral of momentum, or just write it as mv times dv. So this is from the previous derivation. And this is work net, to be more specific. So, and that just turns out to be 1/2 mv squared evaluated from v1 to v2. So, since this is a non-constant force, all we can actually do is apply this to what we have on the graph. So we could just basically take the area under the curve and evaluate this integral, and then set it equal to the change in kinetic energy. So we see that this is a right triangle, so that'll be 1/2 base times height. So that'll be 1/2, and then times 200 times 10,000 and then that equals 100 times 10,000, which would be a million. And then a million joules. So that is our net work. So then we can set that equal to 1/2 mv squared. So the car is starting from rest. I forgot to mention that. 0. So we don't need to take the difference. We could just leave. We can just take the final kinetic energy. So we can multiply 2 by both sides. So that'll be 2 million. Over the mass, which is 1500. So we're just dividing by m on both sides. And then now equal v squared. And then square both sides. And now give you v, which is approximately 36.5 meters per second. Here, let me write that a little bit clearer. Well, we'll just round up to 37. 37